What's happening, folks? Geologist Philip Prince in the Appalachians again today, looking at one of my all-time favorites, the mountain that is shaped like a two. This is called Cove Mountain in Southwest Virginia. And when I say it's shaped like a two, you don't have to take my word for it. Played around with some fonts, trying to find one that matched it pretty well. MV Bowley, never used that one before, but the actual geometric shapes, curves, angles, whatever, they fit this natural mountain feature pretty nicely. About 2 miles from base to the top of the two in terms of ground length there. So it's not a particularly large area, but once you see it in the landscape, you cannot unsee it. I've worked around this place for years now, and whenever I look at this part of the world on a map, all I can see at this point is that two that is mixed in there with all these other mountain ridges. It's just up northwest of Roanoke, Virginia. And when you look at the rest of the valley and ridge, there's ridges with curves and bends in them, but there is most certainly only one, two, again, which is Cove Mountain sitting there. In terms of why this looks like this, that's what we're going to talk about here. There's pretty distinct geologic reasons for it. It is almost exclusively an Appalachian type of thing. But in terms of looking at it today, it's a lot easier than it was many years ago because we have digital topography like you're looking at here. In fact, the first image there in the video was just right off my phone from Google Maps. So you can see the land today in ways that you've never been able to before. And of course, Google Earth alone is a good one. You might be able to see the two now there in the center of the screen, but particularly mixing in digital topography like this LiDAR hillshade just makes the details of just what the land looks like so much more visible than they ever have really been in human history. And all of this is, in many cases, a post 2010 or so thing. Sometimes adding the false color that's based on elevation there helps bring the patterns out for some people. I like that gray hill shade pretty well, but one way or another, having these map technologies allow you to see this absolutely incredible, ridiculous looking landform in ways that paper maps or even the raised relief blister maps, like the vacuum form plastic maps, which are really cool, but they don't quite have the level of conveyance, I guess, that you get out of maps like the ones that you're looking at here. And starting to look at this with more detail, this is a 1 meter LiDAR hillshade. So you're able to see the landscape with exceptional detail here. Of course, the two shape is plainly visible. And if you actually get out on the ground on this thing, you can sort of begin the journey of trying to figure out why it looks like this. And one good way to do that is on the Appalachian Trail, which traverses effectively the entire length of the two. Going southbound here, you're actually going north. Going northbound, as I did in 2006, I through hiked that year, actually right before going to graduate school. You're actually going south, but one way or another, you get a chance to interact with this landform quite a bit, and it actually is home to one of the most iconic Appalachian Trail landmarks, certainly in the South and probably on the entire length of the trail, which is the Dragon's Tooth. Really crazy rock formation of these white sandstone layers that are stood up almost vertically. Going to be talking about what those mean and how they reflect the overall nature of this mountain. All sorts of landmarks around it. If you're on the trail here, you might stay down there at Pickle Branch Shelter. You might buy a Snickers or something there at the Catawba store. But all of these places are ultimately associated with the mountain and the geologic details that are making it look like it does. And as you start to zoom in even closer, we've got it laid out here, kind of looking into the horizon in this case. The yellow line is highlighting the two shape there if you don't see it immediately. You could start to see the layered rock that sort of follows and parallels the ridge. Now, if you're on the trail, you'd be coming along right along the crest of the ridge there. You wouldn't really see what's down in the forest here, but if you could, like you can here when the trees are removed by the LiDAR, it's an incredibly rugged landscape. And each one of those little ribs that you see is a layer of white sandstone that might be a foot or a foot and a half to maybe 3 feet or so thick. So that'd be half a meter to about a meter thick. And the closer you get, the more detail that you can see in that layered sandstone there. And in fact, this LiDAR image is so good, you can actually see the trail as it goes up across those sandstone layers right below the Dragon's Tooth, which would just be off the screen there to the left. So the takeaway here is that the mountain that is shaped like the two is basically made of sandstone. The reason that the mountain is there is that there is a zone of sandstone in the sedimentary layer pack that is making up the valley and ridge that's really resistant to erosion, and it's got softer rocks on either side of it. In this case, there'd be shale on the right and limestone and dolomite on the left. Those are more easy to erode. The sandstone ends up there forming that prominent ridge, and that's a good way to think of it, is that the two is essentially, I mean, it is made of sandstone. And when I say it's a zone of sandstone within the sedimentary rocks, it would be hundreds of feet thick, right? So if you were able to flatten all this out and go from this sandstone layer down here to the last one up at the top of the ridge, you would be passing through literally hundreds of feet, or in this case, probably 150 or 200 meters of rock or something like that. That idea that the mountain is made of this particular rock layer actually shows up in geologic mapping, and the colors that popped up there are the geologic map for this area. This is just the top of the two. Like so many interesting things in the world, the two is where like four different maps come together. Go figure. It always seems to work out like that. But I actually made this geologic map over the course of a couple years, 2017, 2018, finally came out in 2019. It's about to get a final review here, actually, just in a couple months. It was a really interesting experience working around here. And this shot gives you a sense of what the actual top of that two looks like with all of the data on it. So each one of these little points is where I made an observation out in the field. But you can see here that curve of the top of the two, and the geology follows it, or a better way to say that is the mountain follows the geology. So rock structure here is absolutely key, both in terms of rock type as well as how those rock layers have been broken and folded and contorted around. This is a really cool shot because you can see those sandstone layers chopped off at the bottom by a thrust fault. This is actually right up above the Pickle Branch Appalachian Trail shelter. And if you ever walked out to Pickle Branch, you know it looks like they've been, I don't know, blowing stuff up out there or something. There's these pits all over the ground. Those are actually sinkholes in the limestone or dolomite bedrock here in the valley. So limestone and dolomite that can wear away down here in this valley, a lot of shale over on this side that can wear away pretty easily. This really hard resistant sandstone that's actually sticking up there and forming the mountain. All of these ingredients are coming together to produce this really crazy combination of variables that makes this funny looking shape. Now, if you're hiking the AT through here, how much of this can you actually appreciate? Not as much as you would think without a map like this, because for one thing, when you're on the softer rocks, much of the rock is actually covered by pieces of sandstone that have tumbled down off the mountain. And secondly, everything's forested. When you're up on the ridge, you're walking a limited interval in the rock there, and you don't get a big picture like you're looking at here, right? So that being said, when you take the ability to see the overall shape like this, and you take the knowledge that there's erodible rock, the limestone and dolomite on this side, which is older than the sandstone, so it's below, if you will, the sandstone. Erodible shale on this side that's above the sandstone. Got thrust fault evidence here. This thing is kind of bent and kinked around like this. You can pull all this together into a very rational geologic story that makes perfect sense in terms of where this thing is, both in a fold and thrust belt, the valley and ridge, and in the Appalachian Mountains as well. To put that picture together, going to have to draw it in paint. And this is actually going to take a series of sketches because, as we said, it's not every day that you find a mountain that's shaped exactly like a two. Not always the easiest thing to explain, but I promise we will get there. We're going to hop out to paint now and start it up. Hold on just a minute. Okay, so here we are in paint. I'm going to kick this off by talking first of all about that sandstone layer that is sort of the framework or basis for Cove Mountain and its crazy shape, right? So this is going to represent that flat sandstone layer. We're looking at a much bigger area than the thickness, which is quite small. Like we said, 150 meters, 200 meters, 500 to 800 feet or something like that. All right, so step one here, imagine that we take the end of that layer closest to us and squeeze it like this, and it's going to make it kind of fold over itself, right? We're going to make it shorter and ultimately thicker by kind of folding and contorting it into this new shape. All right, so the new shape is going to look something like this. And if we were really serious about this, we would be sure that if we stretch that new shape out, the length of it would be the same length as the edge of that layer at the top there. We ain't gonna worry about that right now. Just a simple illustrative sketch here. You're gonna end up with something like what you see here. It's kind of a crazy looking shape, but fundamentally we've got this kind of curve here. Layers folded over itself back here. And then you got another curve down on this side, right? So the transition there is from this big, wide, flat, unmessed with layer to that same layer, but it's been, again, folded over itself closest to us, if you will. All right, so that's step one. Step two, imagine that the shape you're looking at here gets bent upward. So in sort of in the direction that the arrow is pointing there, we've taken that series of folds, which is kind of like that, and it's going to actually be pushed upward, tilted upward, so it's tilting away from you now very steeply. Okay, we're going to have to draw that again in another paint window, and we're going to draw it from a little bit different perspective, but hopefully it will be recognizable. Okay, step two. We're going to draw that same shape, but from a different perspective. And hopefully it will still be recognizable. So we're looking at it kind of from the back here, I guess you would say. And it's going to have all of those same characteristics that we initially saw in the cross section. But at this point, we need to look at it this way because we're going to try to show what it would look like if erosion came along and sort of chop the top off of it, right? So we'll pretend that this box that I've just drawn there is the Earth's surface. That's the level to which erosion has worn this structure away. And what we're going to do is just draw a line everywhere that layer is going to intersect with that erosional surface. And what we're doing here is actually sort of the basis of a lot of structural geology that is based on geologic mapping of the land surface. You have to think a lot about shapes and geometry and how different shapes intersect with one another to produce a series of lines and curves and things like that. So even though it's geology, it has a lot more in common almost with, like, I guess, geometry or architecture, even engineering or something like that. So you should now see a 2 in the landscape there, and that 2 is highlighting everywhere that folded layer, that set of 2 folds like we initially drew, is touching the Earth's surface. And because that's that sandstone layer, everywhere that you see that 2 is going to be where the mountain forms, right? So getting that 2 pattern is a combination of taking that fold, tilting it upwards, and then chopping the top off of it with erosion. So interesting combination of circumstances there. And at this point, to make this sketch look more like reality, I'm going to remove that line and actually kind of draw the mountain in on top of it. I'm going to speed that up. Hang with me just a minute here. Okay, so there it is. Got the 2 shape, and again, that's a combination of that folded layer that's been tilted, intersecting the Earth's surface. And because it's that single folded layer, that's why those layers of sandstone tend to run along it. And effectively, the 2 is made of a rock layer. It's just a folded and tilted rock layer that has experienced this erosion. And again, because it's in the Appalachians, if you got limestone and dolomite on one side, shale on the other, those are soft rocks. All you're going to see is that sandstone sticking up, and you're going to have that two shape. Now, can you pull this all together into a more, I guess, sophisticated, I use that term lightly, block diagram that shows a little more of the surrounding geology? Yes, that's going to be the final sketch here. So we're going to need one more window. I hope I can make it through this one. I'll do my best. All right, last one here. Going to try to do the full block diagram. And this is going to incorporate really all of those conceptual details that we've talked about so far in terms of the fold shapes, how they interact with the landscape, and what that does in terms of shaping mountains at the land surface. And as usual here, we're going to try to be sure we close all the shapes up nicely, use the fill tool function, and this should end up looking sort of like a geologic kind of map cross-section put together into block diagram format, which is kind of cool to look at. So what I'm trying to do here is lay out just where the different rock types are at the surface, as well as show where they would be down under the land surface. And that whole down under the land surface part can be really challenging, particularly in this part of the valley and ridge, just because its very definition is different layers of rock stacked on top of themselves. And as you've seen here with the number 2, it's possible for those stacking combinations to be pretty complicated. And a lot of what we know about this area is based really just on surface observation alone. And the few times that folks have done drilling in this part of the world, it has always produced surprising results. Now, what does that mean in terms of the 2 structure here? I don't really know. I feel like it's interpretation or understanding, if you want to call it that, based on surface geology is pretty good. Just because there are certain requirements to make that folded layer into that shape, and you have to fit it together with the pieces around it. And fundamentally, what you're looking at here is pretty close, I think, to what you would find if you went and drilled in a particular area. And you should see the same colors here time and again. It should look like that because they've been stacked on top of one another repeatedly to produce the overall stack of rock whose very top you're seeing at the land surface now. So hopefully the icing on the cake here will be to draft in a little bit of topography, and you'll be able to see where the 2 would sit with respect to the geologic structure that we've drawn onto this landscape. So if you could slice the whole thing open, you could see that this is the front of the 2. This is the bottom of the 2 in the base. The dragon's tooth would actually sit kind of right where that dark arrow there is pointing. In fact, this diagram is almost cut as if right through the dragon's tooth. And the last little detail we'll add in here would be the end of North Mountain, which is also part of this overall folding structure, but it's younger rocks, and there's enough shale between it and the 2 that the 2 itself is, of course, the freestanding structure that you see. If you tossed in some what we call form lines here to show how the layers are bent, ends up being a pretty cool looking diagram. And the interesting detail I'm filling in now is that a lot of the shale that surrounds this thing is folded up in all kinds of crazy ways. Sometimes you see that exposed down in creeks. Really cool part of the world to work. And what you're seeing right now, again, was drawn quickly, but this is the same concept that a geologist would be using if they were trying to understand what would be under the land surface and what you might encounter, for example, if you started drilling right there in the middle of the 2. Don't worry, nobody's going to do that. So we'll jump back to the rest of it here. Hang on just a minute. Okay, so that's what's underneath the 2. It's all about that sandstone layer, how it's been bent and folded. And of course, here in the Appalachian Valley and Ridge, sandstone is what makes ridges. So all of the rock around it erodes away. That's why you can think of it in that one layer fashion. And if you bend it and break it apart just in the right ways, get some erosion there interacting with it, you get the crazy pattern that you see here that looks like it almost has to be man-made or something, but is in fact completely natural. If you looked at it in the overall grand scheme of things, that yellow line shows you where that fold pair that makes the two actually sits within a bigger chunk of the valley and ridge. You're looking at about 20,000 feet of folded and stacked sedimentary rock here, give or take. That's about 6 kilometers. Roanoke, Virginia is the city that you see there over at the right side of the image. And pulling something like this together takes years. You're looking at the combined results of studies and maps made by a vast number of people. But it's really neat to see it all come together and try to use it to better explain what all these crazy patterns are that you see in the landscape. And looking closer there, that's again where that set of folds would be. And hopefully that looks something like the sketch that I drew live there just a minute ago in paint. What does this look like from the ground surface? Well, part of that map I made had to climb up on top of Sinking Creek Mountain several times and look back towards Cove Mountain. You sort of visualize the two there, and you visualize the folds sticking up out of the ground. So huge amounts of erosion have been key in revealing what you see in the landscape today. And to try to stylize that, we'll just take a simple set of layers here, stack them up like you see there. This would be sort of the ancient valley and ridge where there's all these fold structures stacked on top of themselves. They haven't been eroded much yet. That's where the two is going to be again. Should be getting familiar now. You're going to see those two folds there. Say you erode it down to that level, that's actually going to give you that modern day landscape. So again, this way of thinking, this way of seeing is the day-to-day for somebody that's trying to do large-scale geologic interpretation in a place like the Appalachian Valley and Ridge. Now, a good question, is there anywhere in the world that there might be a two-shaped structure that hasn't even come up to the surface yet? Probably so, just because it's a very basic set of geologic folds. One that I would throw out would be the Canadian Rockies. Looking there at Mount Rundle, just up above Banff. That's a bigger scale image that shows you where Banff sits in terms of the overall Canadian Rockies. This is folded and thrusted sedimentary rock, very much like the Appalachian Valley and Ridge. It's just not nearly so eroded. It's a younger system. I would say that if you had to guess a place where you might see something like the two, several thousand feet underneath Banff might be a good place. How far? 8,000 feet, 10,000 feet? I don't know, 2 or 3 kilometers. Anybody's guess, but the style of geology that you see in this part of the Canadian Rockies is very similar to what we have here in the Appalachian Valley and Ridge. So in terms of what did this landscape used to look like with the two right there, maybe that's it. But again, nobody knows for sure, and nobody is ever going to know. Fold thrust belts like this all over the world, they make crazy patterns in the landscape. That's sort of their essence, and that's how you can identify them just cruising around the earth with Google Earth, Google Maps, some kind of terrain viewing function. Got Pennsylvania right here. Gonna have to move the box back over here. Pennsylvania Valley and Ridge has some crazy patterns. There is not a two there. You can go elsewhere. Chiapas, Mexico, no twos. Iran, lots of crazy topography, no two. The Marathon fold thrust belt, that's Southwest Texas. Really interesting landscape ridge patterns there. Again, nothing that quite looks like a two. You do see some pretty interesting curves and bends there, but they don't have just the right kind of geologic structure, the right kind of lithologic contrast to make the Cove Mountain two there. So when you see that thing there in the Appalachian Valley and Ridge, it's possible, even likely, that that is the only two-shaped mountain anywhere on planet Earth right now. Will there be others in the future? It's entirely possible. But if you have the opportunity, open up Google Maps, Google Earth, whatever you like, check this one out, give yourself a chance to experience it. It's really cool. Probably going to travel for the next video. Not sure where yet. Either way, hope you check it out.